So in this lesson, we're going to be looking at neutralization reactions and then also looking at what happens with salts when they're added to solution and the reactions that occur as a result. So first of all, let's look at a neutralization reaction. So remember, neutralization reactions are simply reactions that occur between an acid and a base. We've already looked at that. Now we're going to take it one step further because we can actually now, because we know what are strong acids and what are strong bases, weak acid, weak bases, we actually can take those reactions, which are double replacement reactions, and we can actually write the net ionic reaction to see what actually occurs. So keep in mind that strong acids and strong bases, they are going to completely dissociate in solution, meaning they're going to completely break up into their ions. For weak acids and weak bases, we assume that they don't. So they're going to stay together. They're not going to break apart into their ions. So if I were to react a strong acid with a strong base, so for example, Hcl and NaOH, let's actually first write the neutralization reaction, the complete double replacement reaction. So I have hydrochloric acid, HCl, reacting with NaOH. So my products, remember it's innies and outies. So hydrogen is going to react with hydroxide H and OH, which forms H2O. Na is going to react with Cl, which forms NaCl. So your products will be NaCl and H2O. All right? So that's nothing new. We did that in first year chemistry. Now what's new is now we actually have to break apart what's soluble and what's a strong acid or a strong base. So hydrochloric acid is a strong acid, which means it's going to break up into its ions. So it's going to break up into H plus and Cl minus. If it were a weak acid, it wouldn't do that. It would stay together. NaOH is a strong base, so it's going to break up into Na plus and OH minus. Okay? And then NaCl, because you've got a group 1 metal there, it's going to be soluble, so it's going to break up into Na plus and Cl minus, and then water is going to stay together. So keep in mind to write out your final net ionic reaction, you're going to cancel out anything that is the exact same thing on both sides. So my Cl's are the exact same, I'm going to cancel them out, and my sodium ions are the same. And so my overall reaction here is just going to be hydrogen ions react with hydroxide to produce water. All right? So that looks really nice and pretty because you've got H plus OH minus produces H2O, which is what we were told that a neutralization reaction is. You have an acid and a base and it produces water and then a salt. But the salt, because it's still dissolved in solution, we actually ignore it because it has nothing to do with the reaction. Well, what if it's not quite so pretty? So let's look at a strong acid and a weak base. So for example, here I've got HCl and NH3. So HCl reacts with NH3. Keep in mind, this is a little bit different than just a typical double replacement reaction because NH3 is going to stay together. It's not going to be N with Cl and H with H3. That doesn't really make sense. So since HCl is my acid, it's going to produce Cl minus because the hydrogen leaves the HCl and NH4 plus, ammonium. All right, so it's a little bit wonky, but that's fine, okay? I'm going to break up anything that is a strong acid or that's soluble. Well, the only thing that's a strong acid here is HCl, so it's going to become H plus and Cl minus. Now, since ammonia is a weak base, it's going to stay together. I have Cl minus, and NH4 plus is just an ion, so I'm going to keep it like that. Now, notice the only thing that stays the same on both sides are my Cl minuses, so those will cancel. So I have for my final reaction, H plus NH3 produces NH4 plus. Now, on the AP, on a test, on a quiz, on homework, whatever, you only have to write the last line. So if I look, for example, for the first example, HCl and NaOH, I know that HCl is a strong acid, so I know it's going to break apart into ions. I know sodium hydroxide is a strong base. It's going to break up into its ions. So in my head, I already know the net ionic. H plus Na plus OH minus produces H2O. Okay? For the next example, HCl and NH3, I know that HCl is going to break apart. So I would only write H plus NH3 produces NH4 plus. I know the Cl minus is not going to matter. All right, so if you have a strong acid or a strong base, you can ignore the ion that goes with it. So for HCl, ignore the Cl minus. For the NaOH, ignore the Na. For the HCl, ignore the Cl. All right, so let's look at another example. Here I've got a strong base and a weak acid. Okay, so I'm going to show you the entire double replacement reaction, but if we do what I just talked about, NaOH is a strong base, so I'm going to ignore the Na. So here I would just have OH minus reacting with, well, HF is a weak acid, so I've got to keep it together, OH minus plus HF, okay? OH minus is going to steal the hydrogen from the HF, so it's going to become water, plus F minus. But let's see if that's true, okay? So I'm going to write out the whole reaction. So NaOH plus HF, double replacement reaction, you're going to have NaF and H2O, okay? Ines and outies. Break apart anything that's a strong base or acid and anything that is soluble. So NaOH is a strong base, so Na plus OH minus. HF is a weak acid, so it's going to stay together. NaF, because Na, sodium, is a group 1 metal, that's going to break apart into Na plus and F minus. And then you have water. So as I said, the sodiums cancel, and all I'm left with is hydroxide reacting with hydrofluoric acid to produce F minus and H2O. So again, if you have an ion with a strong base or strong acid, you can actually just ignore it because you're going to end up canceling out anyways. All right? All right. So you guys are going to do some practice with that right now, so pause the video. The next thing that we need to talk about are salts. All right? So I'm going to show you examples to show you how to predict how a salt will react in a solution. Is it going to act like an acid, a base, or will it be neutral? So for this problem, I asked you to predict whether the following salt acts like an acid or a base. If they do act like an acid or a base, I asked you then to show the reaction with water. All right, so KF. All right, how the heck can I determine if KF acts as an acid or a base? So here's where you're probably going to have to rewatch this explanation. I have 2 examples you really need to pay attention. All right, so if you look at KF, okay, thinking back to those reactions we just did, where would that KF have come from? What could form KF? Well, I know that the potassium had to come from, because it has a positive charge, it had to come from KOH, the base. KOH, because you can't have KF, KH, that doesn't make any sense. So that came from KOH, and the F came from HF. So in your head, always think, okay, where did this come from? K came from KOH, F came from HF. Well, KOH is a strong base, okay? So if an ion came from a strong either acid or a base, it does not contribute to the acidity or basicity of that salt. Instead, it's going to be neutral. So since potassium ions came from a strong base, it in solution will be neutral. It's just a fact, okay? Don't try and overanalyze it. It's going to confuse you. Just look at it. K came from a strong base. We're going to ignore it. It's neutral. F came from a weak acid. It came from HF, which means it is going to be either acidic or basic. And so here's how I remember whether or not it's going to make it acidic or basic. It's a quick trick, all right? The reasoning is it came from HF, therefore F minus will be a base. But the way that I remember it is the first ion would make it acidic if it came from something that's weak. The second ion, if it came from something that's weak, would make it a base. Acid before base. Okay? So if K had come from a weak base, it would be acidic. If F comes from a weak acid, it would be basic. Well, since F came from a weak acid, this will make the solution basic. Okay, so I have F minus. F minus is going to contribute to the solution. It's going to act as a base. So let's see how that looks. So we talked about base dissociation reactions already. So F minus is going to react with water. And since it's a base, it's going to accept a hydrogen, so it's going to become HF plus OH minus. All right? So let's look at another problem. NH4Cl. So remember, NH4 came from a base, Cl came from an acid. If NH4 came from a weak base, it will be acidic. If Cl came from a weak acid, it will be basic. So what did NH4 come from? NH4 came from NH4OH. NH4OH is a weak base, which means this is going to be a weak acid because remember, acids come first. Cl, what did Cl come from? Well, since it's Cl minus, it must have come from an acid because it would be HCl where it came from. HCl is a strong acid, which means Cl minus is neutral. So NH4 plus is going to act as an acid. Okay, so NH4 plus water. I'm going to have it. Remember, for acid dissociation, I could just break that apart into the 2 ions, or I could have it react with water, and I decided to have it react with water. Okay, NH4 plus is going to donate a hydrogen, so it's going to become NH3 plus H3O plus. The other way I could have written this is just writing NH4 plus produces NH3 plus H+. Either way, it's the same thing. All right, so let's actually look at a problem in which I can actually calculate the pH of a solution that's created by adding a salt. So I add NaClO to water. So I first need to decide, is this going to be an acidic or basic solution and what contributes? So I've got Na and ClO. So Na came from NaOH because Na has a +1 charge, so it had to have come from NaOH. NaH doesn't make any sense. So NaOH is a strong base. So I can eliminate that because that's going to be neutral. ClO came from HClO, which is a weak acid. So ClO minus is going to act as a weak base. So ClO minus is going to react with water. Let's write out our reaction. Since it's a base, it's going to accept a hydrogen, so it would become HClO plus hydroxide. All right? So if you're looking at this now, this is the exact same problem as any base dissociation reaction we've done. It asks me to determine the pH. I know the initial number of moles of ClO minus. Notice all I'm doing is I'm just ignoring Na. So note, whenever you have a salt, typically one of the ions you're going to ignore. So Na you're going to be ignoring, so we'll just plug in ClO minus. That doesn't change anything as far as the concentration is concerned. So if I have 0.6 moles of NaClO, that's how many moles of ClO I have. So I'm going to put my ice chart. I need the concentration, not just the number of moles. So I need to take 0.6 and divide it by 2. So that's 0.30. I'm going to ignore water because it's a liquid, and I don't start off with any HCl or OH minus. Okay? My change is going to be minus X, plus X, and plus X. And so my concentrations at equilibrium will be 0.30 minus X, X, and X. All right? Now I know my Kb, and I can use my Kb because this is a base dissociation reaction. So my Kb, remember, is going to be my concentration of HClO times my concentration of hydroxide times all over my concentration of ClO minus. So I'm going to plug in my values. It's going to be X squared because it's HClO times OH minus all over 0.30 minus X. Now, in order to get rid of that minus X, remember, you've got to show your rule of 100. So my initial concentration is 0.30. I'm going to divide that by my Kb, and that's bigger than 100. Okay, so I can get rid of my X and then just calculate. So my X squared is going to be 9.99 times 10 to the negative 8th. When I multiply 0.3 by my Kb value, which is 3.33 times 10 to the negative 7th, and then I just need to take the square root of that, and I get 3.16 times 10 to the negative 4th. Now note that that's my concentration of hydroxide. And so when I take the negative log of that, that's going to give me my pOH. And so my pOH is 3.50. So to determine my pH, which the question is asking for, I need to subtract that 3.50 from 14, and I get 10.50. All right? So the only new thing here is looking at your salt, figuring out, okay, is it going to act as an acid or a base? If it acts like a base, because ClO minus came from a weak acid, write out a base dissociation. If instead my first ion is the one that comes from something that's weak, it's going to act like an acid. All right? So if you haven't had a chance now, I want you to pause the video and complete the practice problems that are before this part of the notes. And the reason why is because the very last practice problem we're going to use to compare with the example problem we're about to do. Okay? So pause, complete the practice. Okay, so let's look at this example. So here it says calculate the pH of a solution containing. So notice this is the exact same problem as the previous practice problem, except instead of just dissociating your weak acid, you also have a salt there. So let's see how that affects it. So I'm going to write out my reaction. I've got HNO2, okay, and it's going to break apart into H plus and NO2 minus. You could have also reacted it with water and produced H3O plus. It doesn't change anything, okay? So now I start off with 0.085 of my acid, just like before. Again, I don't have any H+, but now I have some NO2 minus. I have 0.10 molar of NO2 minus. So let's see how this is going to affect it. Now notice this section is called the common ion effect. Okay? And we've already talked about this. So my prediction is that because I have an ion that is already in solution, that's going to reduce the ability of HNO2 to actually dissociate. So let's see if that's true. So this is minus X plus X plus X. My equilibrium concentrations will be 0.085 minus X, X, and 0.10 plus X. Now notice really quickly, there's something I skipped over. The salt that's given here is KNO2. Well, why didn't I include the K in this reaction? Okay. Keep in mind, remember I said when you're adding a salt, you will normally get rid of one of the ions. So K came from KOH, so that is going to be strong, so you ignore it. NO2 came from HNO2, which is a weak acid. Okay? And therefore, NO2 is going to act like a base. Well, notice, since you have HNO2 here, its conjugate base is NO2-. So that's why we include the 0.10 molar of NO2- there. All right? So don't let the fact that you have a salt, right, another ion, freak you out and think you have a completely different problem. Just ignore that first ion, and now you just have NO2- and you're good. All right? So now I'm going to plug this into my Ka value. So Ka equals the concentration of H plus times the concentration of NO2- all over HNO2. I'm going to plug in my values. So that's my Ka value. My H plus concentration is X times my concentration of NO2- all over my concentration of HNO2 right there. Okay, now notice I've got a plus and a minus X, so I'm hoping I can get rid of my X, which I can. So I'm going to just be super safe and just take 0.10 and divide it by my Ka value. You could also take the 0.085 value, right? Because you just need an initial concentration. Either way, it's still greater than 100, which is great for us because that means I can get rid of those X's. So now all I have to do is cross multiply and then divide. So I'm going to multiply 4.5 times 10 to the negative 4th by 0.085. Then I'm going to divide by 0.1, and I get for my X 0.00038. Okay, that's my concentration of H plus, which means if I take the negative log of that, that gives me my pH, and therefore my pH has a value of 3.42. It has 0.42 because remember I have 2 sig figs in all of my other numbers, so therefore it needs 2 decimal places. So for the previous problem, that was identical to this, except for the fact that there wasn't a common ion, the NO2-. The pH that you got was 2.21. Now it's 3.42, which means that less of the HNO2 was able to dissociate, which is in line with the common ion effect. The fact that if there's already an ion present, which you're creating by dissociating, then the ability of HNO2 or whatever is dissociating to dissociate is going to be decreased. So HNO2 is less able to dissociate because you already have NO2- present.